Hello, I'm David, in case you've never seen me. Now you know what I look like. I do this because I talk to people in the Maths Learning Centre and they've seen revision seminars and they say, oh, you know, the person in the revision seminars, he was pretty good, and they don't know they're talking to the same person. So that's why I do that. Okay. So this is a revision seminar at Semester 2, 2018, and this is a revision seminar for Statistical Analysis and Modelling, affectionately known as SAM, or possibly not affectionately, it depends how you feel about it, I suppose. I've had some requests to talk about some various things. So I think I might talk about regression, I think, first, possibly. Okay, so regression is actually the heart of statistics. All of the statistical procedures that you meet, maybe not all of them, but most of them, are actually in disguise some kind of regression. And there was an assignment question about it this semester, about the t-test really being regression and that sort of thing. So regression is the process by which we create a formula that predicts an outcome. So this is the idea of regression. We have some sort of variable, which is an outcome. And we might have various other things which I think I could use to try to calculate what I think the outcome ought to be in various different situations. That's what regression looks like in my head. So it could be, for example, if the outcome was, say, a number. This is how I will draw a picture, meaning a number. And maybe there'll be a category of yes or no that will allow me to predict the outcome to some degree, and there'll be some other number that will allow me to predict the outcome, and maybe there'll be some other category. And there, just so you know, that's how I describe the difference between the two main kinds of variables in statistics. There are categorical variables, and I call them numerical variables, but your lecturer might call them quantitative variables, maybe? I don't know. Anyway, there's two main kinds of variables, numbers and categories. And regression is designed to create a formula that allows us to use the information here to calculate what we think this ought to be. It does not tell us whether anything causes anything else. That's not what regression is for, and that's not what statistics is for. It just allows us to make a good guess as to what some number or category is based on some other information. So if information tends to go together, whether it causes each other or not, I should be able to do that. So I should be able to, if this was called y, say, and this was x1 and this was x2, and there's something weird going on there, I should be able to create some sort of formula that uses x1 and x2 and x3 somehow together to produce the answer y. There's some sort of formula here. There's a traditional kind of formula, but that's the idea. Okay, so that's what regression is for. What we try and do is find ways of doing that prediction as accurately as we can. And if we are very clever and use some information about probabilities, we can figure out how likely certain things are as well at the same time. Okay, that's the big idea. And I think to break the ice and give me some time to process what I want to do, I'm going to do a little activity with you. And my activity will go like this. So I'm going to play a game, and my game is going to be, you will tell me either a capital or a lowercase English letter, and I will tell you what the outcome is. And you have to guess what the rule is. So this is the game. It's called Guess My Rule. So my rule is going to take an English letter, which is either uppercase, capital or small, and it's going to produce a number, and you're going to guess what my rule is completely by asking me for some letters, and I will tell you what number it produces. Okay, just give me a second to write down my rule over here. Yep, that'll do it. All right. Tell me a letter. A. A. Which A? Big A or little a? Little a. Right. Capital A. Lowercase b. Capital B.
Lowercase c.
You're doing so well. Someone from further out, give me a letter.
Capital C. You can just write down all of them.
No, you might want to be strategic so that you can get the answer quicker.
Lowercase z.
Capital E.
I'll give you a freebie. Oh no, am I right? Just a second. I think I had capital E wrong. Just a second. So just cut and pick a minute. Sorry, I had them wrong. There we go. Okay, so I have a question. Has anyone got a theory yet? Need some more letters. Ah, did it again. No, I was right about the 3. Sorry. Capital E is 3. Yeah, okay. Sorry.
Lowercase A.
Lowercase a is 4.
Oh.
And it's still 4.
What's uppercase Z?
This is a fun game.
Uppercase I. Lowercase o.
Can I ask a question?
Yeah.
Is there any number that's over 5? Sorry, 5 or above?
No.
Okay.
Yeah. Not even in Greek. All right, so you've got some ideas so far. So I've already got hearing from you that you've got an idea about at least what the spread of the possible numbers could possibly be. You're thinking it's numbers from 1 to 4, and that's a possibility. So we would like to think of some information about about the letters that is allowing me to calculate what these numbers are. That's what I'm going to need. Does anyone have some theories about what information about letters we might use? Sorry? Upper or lower case? So the case could be either upper or lower. Okay. What else?
It's a vowel or not.
Vowel, yes or no? Okay. Number of strokes. Bit difficult to decide for some of them. Yeah, so that's a number. Cool. So we're wondering if these things and possibly some other things that we haven't thought of yet might possibly...
Could you move it up a little bit?
Yep. I'll put my list back in a second. Might possibly allow me to calculate the output. Okay. So do you think that case makes a difference?
Yes.
Yes? And what's making you think that?
Upper and lower cases are sometimes different.
Are sometimes different. Okay. So it's possible that maybe case is making a difference and something else is making the difference back again. That's cancelling it out maybe. That's what's causing the two A's to be the same. Maybe. All right. But it could also be that something else entirely different is causing that to be 4 and it's not case at all. Okay, interesting. I'm going to help you out. It's not the number of strokes, but it is something about the shape of the letter. So what is it that is the same about the two A's and is different about the two E's? Enclosed area, that's something that's different. It has holes in it. All right, so I'm going to help you out again and draw a graph. So this is going to be my output. And this is going to be the number of holes. So some things have no holes and some things have 1 hole and some things have 2 holes. And my output so far could be 1, 2, 3 or 4. So capital A has 1 hole and it's here. Sorry, and small a and capital A are here. Little b has 1 hole and it's here. Big B has 2 holes and it's here. Little c, I should put a grid line on, that would make it easier. Little c and big C have no holes and they're both here. Z is here, capital Z is here. Capital E is 3 and it has no holes. Capital small e is 4 and it has 1 hole. Z, O, I, little o. All right. Now what do you think the rule is? Sorry?
Linear or...
It's some sort of linear? It looks like it, doesn't it?
Linear, but add 2 if it's a vowel.
Linear, but add 2 if it's a vowel. Yeah. So there's this linear thing here where it's equal to the number of holes if you're a consonant, but it's equal to the number of holes plus 2 if you're a vowel. And drawing the graph is what helped us see that, which is what graphs are for. But so what we managed to do is we managed to figure out that it wasn't either of these, but it was a relationship between these 2 bits of information and the output. And this is what doing science with statistics is like. You have to imagine what the variables are. Luckily in SAM, your lecturer will always tell you what the variables are, and you can decide whether they're related or not. And we were able to tell from our graph what the relationship was, but it would be much harder to tell if that difference between here and here was smaller. So if my vowels only added 1, or possibly only added a half, it wouldn't be so easy to tell from the picture what was happening. And the statistics is our way of figuring out how far apart these things are. And I need to try all these different models to see which of them seems to fit and which of them fits the best. And so I need some numbers to tell me how much best it is. Yes, don't question the King's grammar. So that's the philosophy of regression. And I can have as many different variables as I want, creating the output, and I can have as many, but the more of them that I have, the more data I need to be able to distinguish between them. Right, there you go, that was fun. I've been playing with this concept of guess my rule, so thank you for allowing me to indulging me with that. But I'm going to do another one, okay? Okay, so this one I will ask you for a number. Yes, I'll do a few of them. I'll ask you for a number, and you'll tell me, and I'll tell you what the number is that it produces, and you have to guess what the rule is. Okay? And let's just restrict ourselves to whole numbers because my life will be a little bit easier then. Okay, so tell me a number. So this is game 1. Tell me a number.
0. 3.
Someone got a guess for the rule? Times 5? Awesome, thank you. Excellent. So we could do it, you know. Excellent. So ask me a number.
1.
Or
2.
sorry? Yep, that works pretty well. Beautiful. This one's a bit more complicated, so I just need a tool to help me. Okay, cool. Give me a number.
3. 1.
Zero.
I'll give you a freebie. I'm going to go get you to ask 0 again. How about, it might help if we draw a graph. It helped last time. Excuse my use of Excel. Oh, come on, you stupid machine. There's my graph. What's it close to?
Multiplied by 10.
Near times 10. And how is it different from times 10? Sorry? Some sort of random noise. I'm rolling dice on this little dice app here. So it is y equals 10x plus the roll of a die. Okay, and this is what research is really like, because things are not always exactly the same. So we were able to see that if we put y equals 10x on this, this is actually always a little bit above that line. So it's always 10x plus a bit. And if we had done a regression, it actually would have said, it would have given us 10x plus 3.5 as my, if I'd done enough of them, as my graph, because it does it in the middle. So the point I'm trying to make is that what we were trying to do with our brains, statistics allows us to do a little more easily with the tools that it has. And we're always thinking that, well, actually, maybe it's deterministic, maybe it's always the same answer every time. But in real life, it's not always the same answer every time. And we have to deal with the fact that there is a bit of randomness on the end and somehow average it out. And that's the big idea in statistics. And so that's why my formulas for the relationships between things are not y equals, beta 1 plus beta x plus beta 2 x2. They are this and a bit. A little bit of random bit extra. And that's what makes it particularly hard to figure out what these numbers here should be. And that's what regression is for. And so what the process of regression does is it uses some fancy methods. Sometimes it uses linear algebra. Sometimes it uses some excellent computer algorithms that aren't linear algebra, that just keep trying over and over. And what we do is we find the numbers here that make this, on average, as small as possible. That's what we do. So what regression does well, it's a different epsilon for every one of these y's, and so we sort of make it that the sum of the squares of those is as small as possible. But somehow, it's sort of some sort of on average. And that's what it does. And it will tell us what, now the computer, when it does this, will tell us what numbers they are. And under some assumptions, it will tell us what the other options for those numbers could have been if my errors had been different in a different situation. So that's the next layer of statistics. In statistics, everything that you possibly write down or calculate is just one of the things that it could have been. And so there is a real beta naught. There is a real beta naught somewhere in the universe that the machine or cruel David who's playing a stupid game with you knows. And we'll never know what that is. And if it is whatever number we think it is, no matter every time we do this experiment, we'll get a different answer for our beta hats. And we would like to know, based on our beta hats, what could those things be? What options are reasonable based on our data? And that will give us some confidence intervals. But the only way we can possibly calculate those confidence intervals is if we have some assumptions about how the data works. We're going to need to have some assumptions about how this random bit works in order for us to figure out the probabilities of producing these numbers. That's the only way we're going to be able to calculate any probabilities that tell us whether we think things are reasonable or not. And that's why we have the assumptions. So regardless of whether we have those assumptions or not, these numbers will definitely be the ones that make your y's on average closest to this bit as close as possible to the real value of y. That's always going to be true. Whether you believe in the answer you have and what the options are for the true beta based on the beta hats, that requires me to make some assumptions about the things that could have happened, which means I need some probabilities. And so that's why the assumptions are there. So this was me leading up, me playing a game which I think is fun, and I'm using you as a tool, thank you very much. But also trying to make a point about it really is random, but also the x's that you choose aren't random. You chose those numbers specifically because you thought they would tell you something about the process. So the x's when you do the regression aren't random because most of the time you choose them so that you can get it at the actual process that's going on. Because I imagine that those of you chose 0, it was at the hope of getting the constant term. It didn't help in this one, but there you go. Okay, so we got our data, and it will tell us what these numbers, what the closest, best choices for these numbers are that matches most closely with our data, and it will produce for each of them a p-value to say whether you believe the true value is 0 or not. So when you do your statistics in R, it will produce a table that has the name of each variable. Does it say constant here, or does it just say nothing? Sorry? Sorry?
Intercept.
Ah, intercept. Just like there are about 20 different statistics courses, there are about 15 different statistical computer programs in use at the university, so I don't usually keep track of exactly which one does what. So it'll give you a coefficient. I don't know what it will call it, and there'll be a number in each of these positions. And this one would be the beta 0, and this one would be the beta 1, and this one would be the beta 2. But they've got hats on them because they're not the real ones, they're just the ones that I calculate from my data. And there will be a standard error, probably. And there will be a t-statistic. And there will be a p-value. And possibly some other information. There'd be degrees of freedom, no, not in that table. And that p-value is answering the specific question of, do I believe, based on my data, that this number is 0? Yeah. So if beta 1 was 0, then really this isn't even part of the formula, really. And so x1 doesn't have any bearing on the value of y at all. And in the context of our earlier question, how many strokes it has, well, the beta that goes with that is 0, because it doesn't affect the outcome. We thought it might have been there, but it wasn't after all. And so hopefully that would have meant that when we get to, if we did a big regression on that, that it would have produced a high p-value in that row for that variable. Okay, so cool. I'm just making stuff up here, so tell me if I'm just going in all sorts of stupid directions. The betas. No, I was going to say something important. Yeah. The reason we need the assumptions is so that we can calculate this probability. Because we can't calculate a probability without knowing what all of the possibilities are. And so we need to know what all the etas could have been. Not etas, that's not eta, epsilons. All the epsilons could have been so that we can figure out what these things could have been and therefore know the probabilities to see whether they could have been 0 or not. Okay, sweet. Right. So a specific question that we had was how to interpret coefficients, which means I need a specific example of this. Yeah. Would you prefer a different one? Like one that's in an exam or something? No? What would I estimate the weight of? A pig. Yes. Its age and its sex. Okay? Right? And we get this. And the estimated regression equation is the weight equals this age is in years. I should really do them as actually proper numbers that don't look like they're whole numbers. This one's not particularly realistic. I'm making it up off the top of my head. So this is it. My weight is 1.2 plus 168 age plus 5.8 times the sex, where sex is 0 if male and 1 if female. Okay. So if I wanted to interpret these coefficients, I need to interpret the story first. Statistics is always about the story, and in my story I have pigs and the information that I have written down about my pigs is I have written down their age, which is a number. I have written down their sex, which is a category, and I have written down their weight, which is a number. That's what I've written down about my pig, and the story I'm trying to tell is that age and sex can be used to estimate the weight. Oh, this is in kilos, by the way. In kilograms. The age is in years. Okay. So this is the story that we're trying to tell. And we have done our calculation, which is this. So let's put that back. Can we fit it all on the same screen? Yes, we can. And so this is telling us that I put the age and multiply it by 168, and I put the sex and I multiply it by 5.8, and I add 1.2 every time. So each of these coefficients has an interpretation. So I can get part of the interpretation from the maths and part of the interpretation from the context. So let's see. The first, if in the maths, if I need to think, in my interpretation, I need to think about the numbers that I would put in these positions in order to figure out what those things are. So if you were given, if this was the real rule, and you knew that the variables were age and sex, and you were going to guess my rule, if you wanted to know what the constant term was, you would choose 0 for these two numbers. And so this number happens when both of those is 0. So my first step of my thinking is that 1.2 which is the beta naught hat, I'm thinking from the maths that happens when age equals 0 and sex equals 0. That's what that says. And at the moment, these could have just been x1 and x2. There's no particular reason they're called age and sex. But now I take the context and I say, all right, 1.2 is the weight that I expect when the age is 0, so when they're born, because that's what age is 0 means, and when the sex is 0, which means they're male. So we can say that we expect the weight of a newborn male pig to be 1.2 kilograms on average. So we got that from the maths, which told us where that number what we would have to choose for the variables in order to figure out what that number is. And we also got it, then we got it from what the context of what the variables stood for. Okay, so that's that one. So what about the beta? Oh, let's go to the next page. So this 168, which is the beta for age hat. Okay, so let's think about what we would do if we were going to guess my rule based on this. That number there is attached to the number age. And if the only way I can think to figure out what that is to possibly put age equals 0 and then put age equals 1. And keep the sex as 0 so that I can see what it adds when I go up by 1. That's the only way I can think to do that. And so to figure out what that 168 is, I'm going to have to make the age, know what the age is at some point, and make it go up by 1 and see how that changes the output. And so I'm going to say the maths, so I'd know this by increasing age by 1. Now, we might not be able to do that practically in all situations. You might have to increase it by a half and then take that into account. But that's how we would do it. And so our expectation, so we expect, now just a second. So we say that if we have two pigs that are to all intents and purposes are exactly the same other than with their age, if they're different by 1 year, then they will be different by 168 kilograms on average. I mean, that's what that's saying. So a difference of 1 in age, on average, corresponds to a difference of 168 kilograms. All right. One year, because it was measured in years, a difference of 168 kilograms on average. You always put on average. All right, and so my sex, which is my beta hat for sex. Well, my math says that, again, the way that I would tell that would be to make that number go up by 1. So my math says I'd know this by sort of changing the number sex by 1. And changing that by 1, well, that would, let me see, when it was 0, it was female. No, 0 is male, wasn't it? Yes. 0 was male. And 1 was female. So changing it by 1 would go from male to female. And so that's saying that if I switch from a male pig to a female pig, then I expect the difference to be 5.8 kilos. Weigh 5.8 kilograms more than a male pig on average. And probably I need to say for the same age. And up here is like for the same sex. Because really if you change the sex at the same time, then it would change them both. So, yeah. It can be extremely difficult in a context that is unfamiliar to you to do this interpretation. The paradox in exams is you have to slow down. So the reason I've said it this way is so that if you're extremely unfamiliar with the situation, you can separate the maths from the context so that you can do them separately without worrying about them at the same time. So that's how I would interpret these coefficients. In the context of my first game, the coefficient of beta vowel was 2, because switching from a not vowel to a vowel added 2. And the coefficient on holes was 1, because when you went up one hole, you went up 1 for the score as well. Yeah?
It doesn't happen for A or O.
What doesn't happen for A or O? Yes, it does. A and O were up here at 4, but the other number that had one hole was only at 2.
So is the hole's coefficient 2 or 1?
The hole's coefficient is 1.
And then if it's a vowel, you
Add 2.
Okay.
So I'm just going to put this in over here. So our formula is that the y is... Oh, actually, we've got one thing, times 1 plus... So it's 1 times the number of holes plus vowel... plus 2 times the number of whether it's a vowel or not, plus 1. There's a constant term as well. The beta naught is 1. So this has one hole, so the score is 1 hole plus 1, which is 2. Yes, there we go. And this is an A has 1 hole plus 1 plus an extra 2 because it's a vowel.
Doesn't A and capital A have the same vowel?
They do, because they're both vowels and they both have 1 hole.
Oh, yeah.
Yes! My example is vindicated, actually. I'm extremely happy with having done that for my multiple regression. Okay. So, right. Before I move on, I haven't really talked about all that much to do with regression, but feel free to ask any vague or specific question about regression.
Can you go over the test you used to do, like, test all and 0, like simultaneously?
Yep. So far I have talked about, I'm just going to repeat that question for the recording, the test to decide if all of them are 0 at once. Yep, okay. So far I have asked I've pointed out where the p-values are to answer the question of is this one equal to 0, is this one equal to 0, is this one equal to 0. So you may have a combined question of, well, are any of them not 0? Like maybe this whole thing, maybe the best estimate I've got is that when you gave me a number, David just rolled the dice and told you a random number and it had nothing to do with what you said at all. Maybe. And so that would mean that all of those betas would have to be 0. There is a test for that, and it's technically an ANOVA. So what if the question was... What if the question is, are all of the beta, not the beta 0, we don't care about that one, are they all equal to 0 simultaneously? And that would be deciding if my model would be better just random. So the best estimate, if it's random, is just the average of whatever my output is. And go, well, you're going to, on average, give me a number between 1 and 6, so the best estimate I can give you is 3.5, because that's the average of the numbers from 1 to 6. Great. That's what would happen if they're all 0. But if they're not all 0, then you can go, hey, cool, it's actually supposed to be 10 plus that. So we're going to try and combine between them, and there is a test for that, and it's normally done when you do an ANOVA. When you do a regression, it tends to end up down here. Oh, that's the crappest of all crap. You can, of course, read this. You can do it? Yes. Okay. So here is a regression. That's just an ordinary single regression, unfortunately. Pooh, I want a multiple regression. Let's see if we can find one. Right, here is a multiple regression. And here's my multiple regression, and it's got the estimate and the standard error and the t-statistic and the p-value. And so this is saying that yes, this number shouldn't be 0 because the p-value here is extremely small. And so I conclude that yes, there really is a relationship between whatever x1 is and whatever y is. A numerical relationship, it might not be a cause thing. I don't know if it causes it, they are related. And there really is one between x2 and y. And I want to know simultaneously, are both of them 0? And there would be a p-value to go with that, which is down here. There. And it comes from this f statistic here. So this p-value comes from a t statistic, and this p-value comes from an f statistic. The reason they are different is because they are different kinds of calculations. And so the calculation that I do to compare whether I have done a good job of explaining what's going on with my new formula as opposed to just using the mean, and I compare the amount of variation that's involved there using this f, and I get this p-value. So unfortunately, these all look like they're the same, which is not always true. However, it will be true that if this is a high number, then both of these will be high. So if this comes out to 0.75, then both of these would be above 0.05 as well. At least one of them has to be under 0.05 for this one to come out under 0.05. So basically, it if the smaller these two are, the smaller this gets. So I might just write that here. So you look. Yeah, look! I've had a song in my head for weeks, which is from the new film Smallfoot. And there's a line in the song that ends with, yes. When the answers are far away, look closer. Sorry. Look closer. Look closer. So look at the F statistic. So you'll get something like e.g. That's not a real e. That e is not the number e, it stands for times 10 to the power of. And then this p-value here helps you to answer the question. Low, then they're all 0, and high. No, low is they're not all 0, and high is they're all 0. Of course, you never say it that hard and fast. You say, oh, the p-value is above 0.05, and so I conclude that there is no evidence to suggest that any of those are not 0. It's all got to be double negatives here. And for low, you say, well, I conclude that there is a significant relationship between at least one of those variables and the outcome, something like that. That's how they say it in statistics, but different lecturers have different rules for what they find acceptable in the way you say these things. Most lecturers will accept anything that is mostly reasonable, but in statistics, it's like, sometimes it's like there's no right answer, say it how you want, except don't say these, they're definitely wrong. Things like you accept the null hypothesis, you never say that. You say, I don't reject it. Okay. So, cool. Anything else about regression at all?
How that F-test works? I can try.
Yeah, like, because in the normal kind of situation, we do find that test statistic, which is like T equals whatever, and we calculate it using something on a T distribution to find p-value. Is there an equivalent thing for the F statistic?
There is. So I'll repeat all of that. Over in the t-test, you find a value of t and you look it up in some distribution and that gives you a p-value. How does that work with the F statistic? Well, let's see if I can figure out where this comes from. Where does the F stat come from? Where does it go? How do we get that p-value? That's what we want to know. So the F statistic is it's called F. It's named after Fisher, who invented ANOVA. Fisher sort of invented ANOVA in about the 1920s. At some point after that, he came and lived in Adelaide for a while, and then caught tuberculosis and died. Yay, Adelaide. Fisher was very famous in statistics. He invented a lot of what we have today in statistics. It's the basis of a lot of what we do these days. And he was famous for being extremely clever and refusing to explain anything that he thought was obvious. And the tradition in statistics teaching has continued to this day. No, though some of your lecturers, Ben is a really good lecturer. If you're listening, Ben, just take note that I said that. He invented the F statistic. He didn't call it F at the time because that would be a bit too I'm going to call it F after me. But it's based on a comparison of variation. So literally a variance. So the thing that you calculate before you do the standard deviation, that thing. And so what you do is you look at how far everything is from the predicted value. So we have two situations. We have no formula, in which case the predicted value for y is just the mean of y. That's the best thing we can do to estimate it. The best guess we have for what it's going to come out to is the mean. And then we have with our formula we have y hat equals, beta 0 plus beta 1, x1 plus beta 2, x2, like that. And so each of these can give us a distance between the real answer and the one that we predict. So with this one, we'll go the sum of all the distances between the real answer and the one that we predicted. And this one will be the sum of all the distances between the real one and the one that we predicted. And I'm just going to use y bar here instead of y hat so that I can tell between them. And I would like to compare them. So if this does a better job than this does, then there should be a smaller amount of variation here than there is here. And it should be relative to the amount of data we have in both of those situations. So the amount of data that we have here is the amount of data that we have minus 1 for having to calculate the mean. And the amount of data we have over here, now just a second, I might have done this wrong. Oh crap, I always do this wrong. There are degrees of freedom involved, but I've forgotten what they are. Just a second. There's an SS for the model. Yep, okay, got it. Okay, so the thing is that to get to y in this formula, I start with some sort of mean in the middle, and then I calculate these things, and then there's some variation left over after that. And so I have the total amount of data minus the amount of variables I used, because those were information I used to get to the result.
So degrees of freedom here is n minus 3, because there are 3 bits of information I used before I just had random stuff to get to the actual final answer. And this one, the degrees of freedom is n minus 1. And so what I'm going to do is I'm going to figure out how much extra variation I have on top of this to get to here. No, on top of this to get to there. Yeah. And so I'm actually going to subtract these to figure out the difference. I'm going to have the difference, which is going to have a degrees of freedom, which is just 2. That's how far apart these are. The degrees of freedom will be 2, and it'll be like literally the difference between these things. So what I do is I adjust these sums based on the degrees of freedoms that they have. And so this one will literally be, and I do it in that order because there should be more variation here than there is here. There should be more variation just about the mean than there is about the predicted value. Okay? And so what I do is I do this calculation. That's a sum sign, by the way. I think that's it. It's about right. Yep. That calculation there, that is my F statistic. Yay! So these are both variances of some sort. A variance adds up how far everything is from some sort of centre. The centre could be the mean, or it could be your predicted value. And this is a kind of variance, and this is a kind of variance. And when I divide those things, I will get, and a variance tends to have a chi-squared distribution-ish. And when you divide 2 chi-squared distributions, you get an F distribution according to Fisher. And so Fisher says that if you do this sort of calculation, as long as the epsilons are normally distributed, then this will be an F distribution. And an F distribution, a T distribution only needs one number to tell you which T distribution you have. That's its degrees of freedom. An F distribution has 2 numbers to tell you which distribution you have. You need to know how many degrees of freedom were used here and how many were used here. So you need both numbers to tell you which F distribution you have. So this comes from an F distribution with 2 degrees of freedom on the top and n minus 3 degrees of freedom on the bottom. And so you look it up in the F distribution, which looks like that. It's strongly skewed. And it starts at 0 because all of these things are, oh crap, these are squares. These are squares. Everything's squared. Sorry about that. They're all squares. Because if I add up y minus y bar, I'll get 0. Okay. So it starts at 0, it has a hump, and then it goes off like that. I believe the really, really early F distributions don't come back down again. They just go up. But close enough. And you'll go, well, here's my F, and these are all the Fs that are worse, and that's the p-value. There. It has to be one-sided because you can't have negative Fs over the other side. So if your model doesn't do anything, if those numbers are supposed to be 0, then the amount of variation in one should be equal to the amount of variation in the other, and your F should come out to should come out to 0. And so you'll go, oh, okay, cool. 100% chance of this happening, and you'll get a 100% p-value. Yeah, so that's how the F is. But the F should usually, if you've done it right, come out to be more than 1. Because the amount of variation in your new one should be less than the old one. I might have done it round the wrong way. I'm very sorry. I might have done it upside down. I'm making this up off the top of my head. But I was reading this. See how it said 2 and 97? I think the 2 is on the top and the 97 is on the bottom, but I could be wrong about that. It might be the other way around. Possibly up the other way. I will know which way up it really is when I have a look at how the ANOVA works. Have a look at the Anova table.
But that's where it comes from. And so Fisher figured out that if you had normal distributions, then when you did this calculation, that was the distribution you got. Clever. Cool. Now, technically, all statistics can be done, almost all of the statistics that we're familiar with can be done with Fs if we want. It's just that T's are a little easier to understand how the distribution came about. But philosophically, he's just saying, oh, we'll compare the variation here to the variation here. That makes a lot of sense. But the calculation's hard. And so the T is easier to calculate, but makes, in a lot of ways, a lot less sense. So, yeah. Does that answer the question? Okay. Cool. What else was I supposed to talk about? Oh, I will just mention this one last thing before I finish was this. I keep saying that the only way we're able to know what this distribution is based on the distribution of the original. That's why we have assumptions. So the assumptions for regression to work, the assumptions is that generally the kind of formula we've chosen is the right kind of formula. And that's the formula of the assumption of linearity. Because all of this is based on the assumption that it is something times x1 plus something times x2 plus a bit left over, because none of the rest of this makes sense unless that's the truth. And there's always the assumption of independence. And the reason we need that assumption is because otherwise my variances won't work out the way they normally do, because when you add two things that aren't independent and you try and do the variance, you get this wicked covariance thing happening and everything gets messed up if you don't have that. Well, independence, that's just what it is, it's independence. Independence between individual things. And the other one is normality. E is normally distributed. The relationship is linear is equivalent to saying that the mean of the epsilons is 0 as well. That's the other way of saying it. So it has to be, the relationship has to be linear with both of the variables simultaneously, and it also has to be linear with the output as well. So you normally do a plot of the output with each of the variables separately and do a plot of the output with the predicted value as well. That's my understanding, but as I say, things are done differently for different things. And the normality assumption is normally distributed. Usually the normality assumption isn't a problem as if you've got enough data. Yeah. But regardless of whether any of these are true, those betas will be the best betas you can possibly pick. The betas that you choose are not based on the distribution, they're just based on the raw distances between things. It's you only need these assumptions in order to get your p-values right and your confidence intervals right. Okay, sweet. Oh no, there's one more. Homoscedasticity. Is that what your lecturer calls it? Good. He might spell it with a C instead of a K, but it doesn't matter. So the same variance for all combinations of x's, basically. I don't know how your lecturer says it, but the idea is that if the variance is wider in some places than the other, then your distribution won't come out exactly like this because different positions will give you different spread, and so this will be a bit wiggly. Yeah. So really the thing is that these things here are all about being able to assume the distribution of the original data so that you can be sure that this is really the distribution of the F statistic at the end, or the T statistic or whatever it is you're looking for, which means that you can be sure that that p-value is the correct answer for the probability question you're asking. That's why we need the assumptions. That didn't make the slightest bit of sense to me when I was in first year, but I feel better about it now. Okay. Right. Did I talk about Bayes? No, that was in the previous I did a different statistics course this morning, so I'm a bit confused about what I've talked about and what I haven't. Okay. Well, while we're on the topic, I might as well just lick off the ANOVA while we're at it. So, ANOVA. So, ANOVA is basically this F thing. This thing where I compare variances between one idea of the truth and another idea of the truth. And that's why it's called analysis of variance. I call it ANOVA. If you listen to some people, especially in the USA, talking about it, they'll pronounce it ANOVA. And they'll put the emphasis on the an and not the o. Just in case, sometimes it's confusing. Yeah, there you go. And confusingly, in R, they call it AOV. Just annoying. But in R, you just do an LM, don't you? Yep, good. Okay, so ANOVA is not really different from regression at all. It's just that you have multiple categories instead of just two than you had before. So this is the picture that's in my head about ANOVA, and the concept is that you will have something which has multiple categories, is allowed to have just two, but you don't traditionally use ANOVA for that, and a number outcome. This is what ANOVA is for. It's for answering the question of, is this relationship real? So can I predict this based on which group I am in? Well, it's not really can I predict it, but is the outcome different depending on what this category says? So in my head, ANOVA is already a regression-y sort of situation. I might go, oh, the classic is like you feed chicks different diets and you measure their weights. Did they do that example? I don't know. Lambs? All right. So the classic, if you feed these animals these different diets and you see what their weights are. And so the thing is, we're saying, does the diet make a difference to the weight? That's the question that we're asking here. But most of the time we don't pitch our question like that. We normally pitch our question as, if you're in this diet, you'll have this average weight, and if you're in this diet, you'll have this average weight, and if you're in this diet, you'll have this average weight. And we'll say, are those three average weights equal to each other or not? But ultimately, that's just our way of trying to figure out how to ask the question in a way that the statistics can deal with it. So is the outcome different depending on category? That's basically saying, is the mean different depending on the category? And so we'll say, well, mu1 is the mean, mu A is the mean for category A, and mu B is the mean for category B, and mu C is the mean for category C. And we'll ask the question of, are they all the same? With a question mark, but you don't put the question mark when you write it down. The hypothesis is they're all the same, and the question is that the truth? And the alternative is, well, it's not the truth. There are many ways for those to not all be equal. I mean, you could have the A and the B be equal and the C be different, or you could have the B and the C be equal and the A be different, or the A and the C be equal and the B be different, or all of them to be different. And we don't list them all, we just say they're not all equal. All right. So what we have to do somehow is to compare the amount of variation that comes about by attempting to predict based on category to the amount of variation that comes about by not attempting to predict based on category. By going, Yeah, they're all the same group. It's one big mean. So in my head it goes something like this. This is the category. This is the outcome. And every individual sheep or chicken or whatever it is will be a dot on this picture. And there are 3 categories, A, B, and C. And I can put a dot to say where my chicken or thing is. And I might have to spread them out a little bit sideways so that they're not on top of each other, my dots. So something like that. And so when me looking, I'm going to rub one of these out. So looking at this picture, didn't work. Looking at this picture, I would probably just looking at it conclude that the ones in group C tend to be lower than the other 2. Maybe there's not that much difference between A and B, marginally, but really not that much. So the question I'm asking is, does it matter which group you're in as to what the score is? So if I instead combined all these into one big category, all these A ones would be like here, and all these B ones would be like here, and these C ones would be like here. Yeah, sorry. And the C ones would be like there. And I would like to know, could I guess which category they were based on the number that they got? And there's actually a dark patch here and a dark patch here, so there's 2 separate clumps. And I'll be able to tell, based on these clumps, that there should be 2 different groups, if I was just looking at the data. Okay, so does the category make a difference to the outcome? Is saying, well, could I, from the outcome, tell which category I was in? That's the same question, really. So in this case, I could. I could tell if I was in C, but I wouldn't be able to distinguish between A and B. And so what I'm thinking is that there is a grand mean of the entire big group, and the amount of variation that's going on here is however much variation there is around this line. But over here, I'm thinking, well, I'm supposing they've got different means, and each of these has their own mean. And there's an amount of variation there, assuming that that's what the real mean is. If the mean of C really is where I think it probably is, if I do the variation around that, and the variation around this, and the variation of this, and add them all up, that should be less than the amount of variation I do here. And I'm going to compare them to each other. I'm going to divide one by the other. And so I want it to be a big number when there's more variation. No, wrong way around. I want it to be a big number when this is better. And so I should do probably this variation divided by that one. Yeah, I had it round the wrong way. Sorry, before. But I will just check in the Anova table. But I do also want to adjust for how much data there is as well. Okay. So to figure out where so now I'm going to go back to my original model, and my original model is that when the universe figures out the weight of one of these chickens, it says, ooh, well, so which feed did it have? Excellent. And so now on average there'll be this, and then there'll be a bit of randomness on top of that. Right? Somewhere there's a big angel that has the book of distributions, and this is how they're doing it. Okay? The keeper of the distributions decides this is what is going. Or maybe the universe isn't like that, and they just go, don't tell me, who cares what the feed is? It's just this. Okay? So that's what we're doing, and so we're going to compare to that. So we're going to say to imagine to get to a feed, first we would have to get to the average for that feed group, and to get to the weight we would have to go a little bit above or below that. That's our idea. And so here we have the grand mean. And we would have to get from the grand mean to the group mean, and then we would have to get to the actual value. Yeah. And this is how far the actual value is from the grand mean. And this distance here is the one that that's bad. This distance here is the one that we calculate to do the overall standard deviation or variance. And this is the variation that's caused by being in a different group. And this is the variation that's caused by just being a different chick or lamb or whatever it is that I am. So this amount of variation is the SS total. Do they call it T? Yep. This is the SS for the model, and this is the SS error. SS stands for sum of squared differences, because I'm going to square those differences. Okay. So the magic of variance basically says that if you actually add up all the sum of squared differences here and the sum of squared differences here, it comes out to the total, which is really cool. You wouldn't expect that to happen with all those squares going on, but it does. So if the null hypothesis is true, then this bit here doesn't actually make any difference. Being in a different group doesn't make a difference to what your mean is. So if the null hypothesis is true, this bit here should be approximately 0. And so when you divide these two, these should be roughly the same. And if the null hypothesis is false, then there should be a difference based on the group mean, which means that this isn't 0 and this is definitely smaller than this. So I'm pretty sure we actually compare these two. Yeah, okay, cool. So here's the thing. If this is really tiny, then we won't be able to tell it's different to 0. But we only really need it to be tiny relative to this variation. So if you look over here, if these groups were much more tightly clustered together, it would be easier to tell them apart, even though the means are the same distance apart. And so I actually have to compare the amount of difference between the means to the amount of difference between the individuals within a group, basically, how far everything is from the mean. So I'm going to say, hope that this is bigger than this. So I want to go this divided by that. So I did have it right in the first place. Actually, no, I didn't. That difference should have been on the bottom. Oh, fuck. What did I have before? Yeah, the difference between them. So I want, yeah, that should have been the other way around. This is the difference between your thing and your model. This is the individual and the model. That's supposed to be on the top. So, yes, it is the other way up. It's definitely up the other way. Okay. Okay, so what we want is we want the SSE to be greater than the SS, to be less than the SSM. Oh, damn it. No, I was right to begin with. Oh, I always get it wrong. But I definitely want this. I want this to be bigger. I want this to be bigger than that. And the reason I want that is because so that the amount of variation in the groups doesn't distract me from how far apart the means are. So if these groups are really far apart, then I'll be able to tell the difference between them just by looking, not even knowing what the groups are. So I just want to do this. The difference is that if I had the means like this, and there are only this amount of variation around them, then when I put them all together, there'll be gaps, and I can tell which group is which. And so this one, the SS model, which is the difference between the groups themselves, is much bigger than the SSE, and that's yes. The means are different. But in this one, there's so much variation going on that if I clumped them all together, I wouldn't be able to tell who was in what group. And so this one, the SSM, is less than the SSE. And so the means are the same. Well, they might as well be. I can't tell. Right. And I know that I divide these things to get my F. And so I'm going to, and I need my F to be big on my picture. and so therefore I need to, if I want to get the conclusion of different, I need my f to be big, so I'm going to go SSM divided by SSE. Okay. SSM divided by SSE large would imply a difference between the means. And so that's the one I want. Cool. Only I'm not going to do SSM divided by SSE because I need to take into account how much information I've got. Right. Nearly there. So with this one, with 3 groups, this SSM, I have actually included the difference between the grand mean and the group mean once for every individual in the set. I've done that for every individual in my data, but but there's really only 3 group means. And so there's only 3 bits of information there. So I need to divide by, well, degrees of freedom is always 1 less than the amount of data you have. So 1 less than the number of groups. So I'm going to have, actually, this isn't what I really want. I actually want to go, the SSM has a degrees of freedom, which is the number of categories minus 1. And the SST has a degrees of freedom, which is the number of subjects minus 1, because that one's just how far everything is from the mean, and that's, I always do an n minus 1 when I do an ordinary variance. And then the SSE, the degrees of freedom is, well, the difference between those. It's the number of subjects minus the number of categories. Right. And so instead of using SSM and SSE, I need to take into account how much information I've got. So I'm going to divide this by that to get MSM, and divide this by that to get MSE. So SSM divided by its degrees of freedom is the MSM, and SSE divided by its degrees of freedom is the MSE. And then the F statistic, oh crap. And then the F statistic is the MSM divided by the MSE. Yeah. Really hoping I've got that right.
Isn't the DFD equal the number of subjects, take the number of categories, take 1?
No.
So they've got a sum, the degrees versus sum.
There's, yep, so this plus that, just wait for the light to change. This,
All, like, it's hard to make it very hard to estimate all the coefficients underneath.
yep. These 2 numbers do add up to that. So if I go categories minus 1 plus subjects minus categories, the categories and minus categories cancel out and I get subjects minus 1. I mean, you just arrange them to add up. I'm not sure if there's any more meaning to it than that. There probably is. But yeah, you've got all the subjects and you want to figure out how far they are from their group means. So I subtract how many group means there are. Whereas this one is all the all the categories, and I want to know how far they are from the group mean, and there's this many categories and 1 group mean. And this one is I want to know how far the subjects are from the group mean, and there's this many subjects and 1 group mean. Yeah, that makes sense. This SSE is how far the subjects are from their group means, and there's this many subjects and that many group means. I've never thought about it that way before. That's much nicer. I like it. Yeah. These are the things, and we want to know how far they are from those things, and we count how many of them there are. That's extremely mystical, and there's some sort of fabulous linear algebra orthogonal projection thing that makes that work. So. Yeah, you see how I did this? I actually did these 2 because I knew that they were definitely true, and then this one is how far apart they are. Yeah. And that's how you figure out the F. And that F will come from an F distribution with number of categories minus 1 on the top and number of subjects minus number of categories on the bottom. Because those are those degrees of freedom that I use to calculate them. And I'll look that up in an F distribution and find the probability, and ta-da. Right. So in an ANOVA table, you tend to see them all Yep. In an ANOVA table, oh good, I got it right. Okay. You tend to see them set up like that. So this is the one for regression, but it's the same for ANOVA with groups. It's just that the K. This one's for regression, isn't it? Yeah, that one's for regression. So with regression, for the regression, the K is the number of variables involved, which is one more than the number of categories you have. So here's how we connect those together. Just in the table. So it's this number divided by that number goes here, this number divided by that number goes here. We know that this plus this equals this, and this plus this equals this. And this number divided by that number goes there. Yeah. So I don't know what your lecturer does. Some of the old lecturers used to give you an ANOVA table with some holes in it and tell you to figure out what the missing bits were. So they go, oh, they'll tell you this one, and you go, oh, well, then that would mean that this is the difference between them. And you can figure out all of these from the data. And so they give you some missing bits of information and you'd figure out the rest from there. So I don't know if your lecturer will do that sort of thing, but it's something that lecturers have done in the past. So how is this regression? Well, the thing is that our model is... Look closer. Our model goes that the output is... pick the right mean that goes with the group you're in, and then add some error. That's our model for how the universe finds out what the weight should be. And that is not the kind of model that we can actually write down in any reasonable sort of way. And so one way that we deal with this is we go, well, that's okay, because what we're going to do is we're going to have some sort of grand mean. We're going to have the mean for one group, and then we'll add a bit of extra for one of them and a bit of extra for the other one. And so we'll actually do it like this. The mean of like group A plus the x if you're in something to say whether you're in group B or not, plus something to say whether you're in group C or not. We're going to do something like that, where xb is 0 in group B, sorry, 1 in group B and 0 otherwise, and xc is 1 in group C and 0 for not, which means that if you're in group A, you're not in group B, so you've got a 0 here, and you're not in group C, so you've got a 0 here, and so you end up with mu A for the mean. But if you're in group B, you have a 1 for this and a 0 for this, so you end up with mu A plus this number is whatever the mean is for group B. And if you're in group C, you end up with this plus that. So the idea is that there's 3 groups. You actually only need to know which of the 2 groups, the other groups you're in, because if you're not in those, then you're definitely in group A, and so you actually only have 2 variables. Yeah. There you go. So it's not number of groups minus 1. There's actually 1 variable for each group. One of them is the constant term, and 2 of them are regression coefficients for those things there. So we actually end up with, so if in A you've got y equals mu A plus epsilon, if in B we've got y equals mu A plus this, which comes out to mu B, and if in C we get y equals mu A plus mu C, plus epsilon.
which is mu c plus epsilon. So what we do is we arrange for these betas to give me the correct means, basically. So that's how we set it up as a regression. And that's why when you do it as an LM, you only get 2 rows, even though you've got 3 groups. Well, you do get a third one, which is the constant. And that constant is the mean of whichever one the computer decided was the base group. And it will usually do them in alphabetical order if you don't give it another reason to do so. And in science, you would normally do like a control group. So you would have, well, these ones are on what we usually do, and these are the different ones. Or these are the people who haven't got any treatment at all, like they've got a placebo, and these are the ones with treatments. Or this is what we used to do, and this is the ones we're going to do now. So usually there's one that it makes sense to compare everything to that one anyway. Yeah. So if I was going to interpret the regression coefficients that came out when I did an ANOVA via an LM, that's how I would interpret it. I would say the mean for group A is whatever the intercept is. The mean for group B is intercept plus whatever the coefficient for B is. And the mean for group C is whatever the intercept is plus whatever the coefficient is for group C. Yep. Right. So you may notice there that I'm out of practice with choosing which way up an ANOVA should be, but I was able to reason it out based on what I knew ought to happen. I knew that my test statistics should be big to give me the answer of everything's different, and so I needed to divide them in the order that made them bigger when I got what I wanted. And that was the decision I made to get where I wanted to go. Cool. All right. Any, well, ask a question about this or something else. Or tell me to stop.
Could you write up what all the MSC and MSN, all that stuff actually stands for? Because I got the world for it.
So let's run through all of those. So the SS total is the sum of squares total. The SST is sum of squares total. And that means that it's a sum of something squared. And the thing that it's a sum of something squared is a difference between your data and something else. And it's between your data and the grand mean, the total mean. The SS model if you look up in another textbook and online resources, it might say SSG for group. So this is how far the model is from the grand mean. So in the context of ANOVA, it's the local mean. The y bar for your group minus the grand mean. So that's in the context of ANOVA. Okay. Yes. And the SS error is how far your individual is from the model. Because that's how much your model is wrong. That's why it's the error. So this would be the regression version, and this is the ANOVA version. Okay, so I need to write that thing I said. It's how badly wrong the model is. That's why it's called the error. And so that's why it's the distance between the actual value and what the model says the value should be. The actual y and what the model says, which is the y hat, or the group mean. Right. Do you want me to do the other ones, the DFs and the thingies as well?
Yeah, why not?
So just to repeat myself, the DFT is the degrees of freedom total, which is the number of subjects minus 1. The DF model is the degrees of freedom for the model, which is, in the context of regression, it's the number of coefficients, including the constant term. And in the context of ANOVA, it's the number of groups minus 1. So, and it works on the same subtraction method as this one. This one is how far every individual is from the center, and there's this many individuals and there's one grand mean. This one is how far all of the model pieces are from the grand mean, so there's this many groups and there's one mean. And the last one is how far would be the number of subjects minus the number of coefficients, or the number of subjects minus the number of groups, or categories if you like. So this is how far the subjects are from the model, and the model is which group you're in, and so there's this many subjects, and how far is that from the number of groups. And then the mean square for the mean will be the SS for the mean divided by the degrees of freedom for the, not mean, for the model. And the MSE will be SSE. Mean square for the error, which is SSE divided by DFE. Right, okay. Statistics is nothing if not full of TLAs. I should have worn my TLA t-shirt. 3-letter acronym, which is itself a TLA. Right. I suppose the only thing, if I'm going to do this properly, is to do the assumptions. So I might as well put them down. Well, there's always independence. And technically there's sort of 2 layers of independence here. You want sort of the groups to be independent of each other, and then the individuals to be independent within the group. Yeah. So basically what that means is when you've got your category here, the important thing is to make sure that your sheep or people or chickens or cars or whatever they are all in different groups from each other. It's not like you have it's not like everybody's in all three groups. That would be not independent, because you have repeated measurements on the same individuals, so they're not independent from one group to another. What's the next one? And independence and normality. That's about it for ANOVA, because you don't need linearity because the... Sorry? Oh, yeah, equal variance. Gotcha. Linearity doesn't matter because all of my variables are just 0 and 1, and that's automatically going to work fine. We don't have to worry about that. So we need normality. It's normal within each group. And what that will do is it'll guarantee that the epsilons are normally distributed. And homoscedasticity. In all groups. The rule of thumb I was taught for, so these two, that one you can only check from the story. This one you can do a QQ plot of the residuals. So that would be with a QQ plot. And this one, I was always taught that you just take the biggest variance and the smallest variance, and if the biggest one is no more than 2, I do it with the standard deviations, not the variances. The biggest standard deviation is no more than 2 times the smallest standard deviation, then you're okay. So and that in itself is a hypothesis test of its own. Because standard deviations come from a chi-squared distribution, and when you compare 2 chi-squared distributions, you get an F, and 95% of Fs are less than 2. And that's where that comes from. It's a hypothesis test all by itself, which I also didn't learn until I did like second year stats. I haven't done third year stats, so I don't know, it could have been there too. Yeah. So again, choosing what the correct means are in each group doesn't require you to do these assumptions because they're just averages. Being able to calculate your p-value, that's what requires those assumptions. Yeah. And your overall ANOVA p-value, when you do it as an LM, comes from that final bit right down the bottom where it has the F statistic, because essentially you're saying that both of these, wherever it is, I wrote it down here somewhere, that both of these have to be 0. So it's equivalent to the same thing over in regression. Okay, well, that's 3 o'clock. The recording is going to continue for another half an hour if you want me to keep going. You may want to not have the embarrassment of calling it out and come down here and do it with me now, but I'll still record it so that you can find it later. Or you might want to yell something out and say, David, there's still something on the board you haven't talked about yet. Or I might be too tired and I might stop. We'll decide. So, anyone want to talk about anything or tell me something that I did was wrong? Oh, what is this? What is it? That's the question. Well, that's an excellent question.
let me just find a better picture of it for you. There it is. Only that one's backwards from this because, of course, when you put it on a t-shirt, you have to iron it on backwards. What do you notice? So it's tetrisy. They're made of squares. How many squares does each colour have? 7. Yeah, that's not important, but it's still cool. You may or may not notice that there is no black line here or here. And that's important because that means that the yellow bit joins onto the other yellow bit, and the red bit joins onto the other red bit. So it's not 9 regions; it's only 7 regions. So look at the yellow region and tell me how many of the other regions it's touching. What was that? It's touching all of them. In fact, all of them are touching all of them. The green one, for example, along the bottom touches this purple one and this blue one at the other end because it wraps around at both edges, you see. So when something wraps around at both edges like that, it's the same structure as the surface of a donut, a torus, if you will. Because if you wrap it around one way, that makes a tube, and then you wrap it around and the tube joins to itself. So on a torus, it's possible to draw a map so that if you want adjoining regions to be different colours, you need 7 different colours. But on a ball, you only need 4. Yeah, and this was proved for the torus several decades before it was proved for a sphere. And the sphere one was proved with the help of a computer. And that was the first thing that was ever proved with the help of a computer that people accepted was a proper proof. Yeah. So that's what the t-shirt's about. There you go. That wasn't at all related, but it was fun. That's got a little Easter egg on this revision seminar video. So Maths Learning Centre is open all the way to the end of the exams, including, for example, on Monday and or Tuesday next week, depending on when your exam actually is, that I can't remember. So don't think that when we get to the end of this week, you can't come and talk to us about stuff because we're still going to be there. So feel free to pop in and have a chat if you want to talk more. Thank you. Second. So you're saying that somewhere near the beginning we had...
It was the table that had like the beta 0, beta 1, all of that, and then you had the statistic thing at the bottom. Yeah, there.
Yep.
This bit where it has the...
Oh, crap. Right, this thing here.
Yeah.
Yep.
The, where you had the F bit at the bottom.
Yep.
Do you actually, does that needed? Because if you had all the other ones that say it's not, because this over here proves, says like, oh, it's beta not 0, it's beta 1 0. Is that needed then? Because that kind of tells you if they're all 0?
That's a really good question. And the answer is more of a philosophy thing. So philosophically, if every hypothesis test you have has a 5% chance of being wrong, like if you reject it, you get a 5% chance of being wrong.
Yeah.
And the more of them you do, the more chance you have of being wrong.
Oh, okay, yeah.
And so you do the overall one just to check before doing the other. Because if the overall one comes out as, no, they're all 0, you can stop. You don't need to look at all of them. And then you've technically only done 1 hypothesis test and not 3.
Okay.
That's, as far as I'm aware, that's it. But the question is extremely valid. Because, right, if any of those come out as under 0.05, then so will the overall one. And so I think there are some bits right on the edge where it can be in doubt as well. But, yeah.
Okay.
In essence, it's more like, which question did you want to ask? and the F, if the question you're asking is, does this model do anything? Then the quickest way to get there is to go direct to the F.
Yeah.
And it's just an efficiency thing, I think, in the end.
Okay.
I'm sure if a statistician was listening to this, they would run down and slap me because there's probably really good reasons. But in the end, it's an efficiency thing.
Yeah.
So, and then that's important for an exam, right? Because you could go, oh, I only have to look at this number, and then have to decide for all of them.
Yeah.
Yeah.
And with the number of subjects, is that the number of subjects in total? So if you get all the subjects from group 1, all the subjects from group 2? Okay.
Because the big idea is if which group you're in doesn't make a difference, it's really just one big group.
Yeah.
And so, yeah, you lump them all together into one great big group.
And you kind of see if that works, and if it doesn't work, then you've got contradiction.
So that's the total number of subjects.
Yeah. So ANOVA, you kind of use contradiction to prove...
I mean, it's all contradiction.
Yeah.
All hypothesis tests with the p-value is technically like a probability version of contradiction. You say, well, if it was this, then this would have happened, but that's unlikely, so it's not that.
Oh, okay. So you're kind of go a really roundabout way.
Yeah. And some people who use statistics, modern statistics, it's been invented like in the last 20 years instead of in the last 100 years, feel really uncomfortable with that, and they use different kinds of statistics so to get around having to do that. But in the end, it's a decision-making process, and it's not the worst one.
True.
But yeah, so that's why the p-value, you're looking for a low one, because you're trying to say it's unlikely so you can do your contradiction.
Yeah.
Yeah.
Okay, yeah. So it's unlikely that this is going to happen, so we're all good to have it happen.
Yeah, because we didn't want it to happen. So yeah, it's like, if this was all 0, then this wouldn't have happened. That's good. I didn't want it to be all 0 anyway.
Yeah. Okay.
So, yeah.
I think I'm with you. I think I got it.
It takes some getting used to.
Yeah, it's weird to get your head around, I think.
Yeah. Hypothesis testing is that big, there's a lot going on, and one of the big things is that it's all proof by contradiction.
Yeah.
Only with probabilities, which makes it worse.
Yeah.
So, yeah.
Okay.
Cool.
Thank you so much.
You're welcome.